All right, we get to this beast of a chapter now. Chapter 16 has kind of a lot to it. We'll try to curate it a little bit and make connections where we need to, but it's kind of just a lot of content and a lot of calculations. So we'll do our best. It's kind of a catch-all aqueous equilibrium chapter. A good amount of it comes from buffers and titrations. The nice thing about that is that buffers and titrations are pretty much the same type of calculation, okay, for a lot of it. But then we have also got solubility equilibrium sort of thrown in here. But it's just an example of an equilibrium problem. Not much new information, but an example of a type of equilibrium problem. But the buffers and titrations and stuff is new information for some part, but it relies pretty closely on our knowledge of how ions exist in solution. So when we were identifying the acidic ion or the pH neutral ion, okay, that has a good amount to do with it. So you've probably heard of a buffer before. Buffers are important biologically. Where have you heard about a biological buffer? The pH of your blood. Yeah, the bicarbonate carbonate buffer is what maintains the pH of your blood. Okay? So pretty important. Okay? If you own a pool or spa, it will be buffered to resist changes in pH. Every consumer product, every soap or shampoo or something that you use, is buffered to maintain its pH within a certain region.
So I take it it's easy to buffer something?
Yeah, absolutely. You just have to add the right stuff. Okay? You just have to know what to add, but yeah, it's not difficult. And it has two components. Every buffer has two components. Okay? Because we resist changes to the pH of the solution, we have to resist changes from acids and from bases. Okay? So that's the key to a buffer. It resists changes from both directions, okay? And sort of keeps us within an acceptable window. So let's start with a normal weak acid equilibrium. We've seen this many, many times before. Okay? Let's do Le Chatelier's principle. Which direction will this reaction shift if we add more conjugate base? Yeah, reaction will shift. If we add this, we're going to produce more HA and water to compensate for that, to reestablish the original equilibrium that we had. Okay. What happens to the acidity of this solution? What is the one ion in this equilibrium that makes that establishes the acidity of this solution? Yeah. Okay. So look at shifting that way will consume hydronium ions. Okay. So it becomes less acidic as we consume what direction does that take the pH, though? Yeah, pH up. Okay. Percent ionization is really this concentration divided by the original acid concentration. Okay. So what happens if we're shifting that way? What would happen to the percent ionization? Yeah, think of it as making more intact HA molecules. Okay. Okay. So what we've actually done here is took a weak acid, think of something like acetic acid, so vinegar solution like that, and to it we just dumped in some A minus, so acetate. So if we added some sodium acetate, the conjugate base of the weak acid that we started with. So now what we end up with is a solution that has a good amount of weak acid, actually intact weak acid, okay, as well as a good amount of its conjugate base, okay, the acetate ion, for instance, in the case of acetic acid. This is different from any of the equilibria that we saw before, because in just a regular weak acid, it's mostly over here, and it ionizes a little bit over here. And these would be equal, right? Those would both be X, right? Just at a normal equilibrium, okay? But it's different when we purposely add more of this in, okay? These two aren't going to be equal anymore, okay? We're going to have a good amount of this and a good amount of that, okay? So what we end up with is equilibrium concentrations of the acid and its conjugate base very close to their initial concentrations. If percent ionization is low, that's when we can make assumptions about, original conditions, right? That was our X is small assumption. If there's low percent ionization, then we don't need to subtract the concentration from the original. We just sort of say what the original concentration was, okay? So the Ka equation for this one right here would be what would go on top of that fraction. We're just doing concentrations of these things. Yep, the hydronium and the conjugate base. And then the bottom would be, yeah, and it would just be HA, not water. Okay. These would be at equilibrium, but there's actually, in this case, no need for an ice table if we're assuming the equilibrium concentrations of those two are pretty much the same as just what we put in. Okay? Then we don't have to do minus x and plus x and stuff like that. Okay? If we're just assuming original equilibrium. If I solve this for hydronium, it is Ka times the acid, HA over A minus. Okay. If we take the negative log of both sides of that, what is negative log of hydronium? pH, okay. What is negative log of Ka? What is negative log? We called the negative log a function. That's the p function. Okay. So we add or subtract when we're taking the log of things that have been multiplied together. Okay. So that fraction. pH. And then we could do minus the log of that fraction. Or if we switch the sign, you can invert that fraction inside there. So it's actually plus the log of the A minus over HA. It's just a sign change that happens inside of that log. So a couple of rules of logarithms. Okay, so that equation is written right here. That is sort of the equation, the main equation of this chapter. It is remarkably simple. Okay, pH equals pKa plus log concentration of base over acid. Okay? That's not a difficult calculation to do. Okay? It requires no x's or adding or subtracting or anything like that. But, so the difficulty in this equation is not using it. Okay? It's an easy equation to use. The difficulty is knowing when it is appropriate to use this. Okay? Any of the mistakes made with this equation involve circumstances where this equation is not appropriate, in other words. Okay? So, this only works for a buffer solution. We're going to define a buffer solution as a solution that has high concentrations of both parts of a conjugate acid-base pair. Just what we were describing before. If we say start with a weak acid and then add its conjugate base to it. Okay? There's no neutralization or anything that happens. They both end up just sitting there. Okay? So if we have acetic acid and acetate, or HF and if F minus, okay? If we have both of them. So that requires putting both of them in the solution. Okay? You have to have high concentrations of both. They have to be a conjugate pair. It doesn't work if they're not conjugates. Okay? So be careful. This is the Henderson-Hasselbalch equation. We better write 4 buffers right there, because that is an equation that is just begging to be misused. And there are a lot of complicated circumstances we're going to talk about, like adding a strong base to a weak acid solution. Okay? Different things happen, and we have to take that step by step. Okay? This is only when we have an established buffer solution. Okay? Don't flip that fraction, even though before we had that fraction upside down, we were doing the minus log. Okay? So this equation will always be shown as plus log of the conjugate base over the conjugate acid. Okay? The pKa, right? It's an A, so it is the pKa of the conjugate acid, okay, of that pair. So if you have a Ka, right? We typically in chemistry have tables of Ka values. What do you have to do to get pKa? Negative log. Okay? Chemistry in inorganic and physical chemistry, we like Ka values. In organic and biochemistry and biology, they just use pKa's. Okay? Because a lot of times when you're dealing with buffers, the pKa is just what you need to use. Okay? So, if you go on to take a biochemistry class or anything like that, it's all going to be about pKa's. Even for organic chemistry, we use pKa's quite a bit. Okay? We don't do calculations with them. We use their values, though. We compare their sizes. So, it's actually not that bad. So, this makes things a little bit easier for us. We have a solution that is 0.50 molar acetic acid and also is 0.50 molar sodium acetate. Okay? Acetic acid is just a weak acid, right? HC2H3O2. Okay? Sodium acetate is an ionic compound that has the sodium ions and the acetate ions. Okay. But because the sodium ion comes from sodium hydroxide, a strong base, what does that mean about the sodium ion in an acid-base solution? Think of it this way. If sodium ion were to have any kind of acid-base properties, what it would be doing was making sodium hydroxide. Okay? But you can't make sodium hydroxide. Sodium hydroxide is a strong base that just releases. So what does that mean about the sodium ion? Sodium ion is pH neutral. We cross it out. Okay? The sodium ion is a spectator ion here. It has nothing to do with what we're actually doing. What we have here is acetic acid, the molecule, and the acetate ion. What are their relationship with each other? They are conjugate acid and conjugate base. Okay? But that's important. The only thing that's different between them is an H plus, essentially. Okay? The acid has lost an H plus. That is its conjugate base. Okay? Acetic acid is a weak acid. Its conjugate base will be a weak base. Okay? Don't be thinking that those things are opposites. Right? A weak thing will make another weak thing, okay? At least in terms of what we call weak. Okay? So we have a solution that's 0.50 molar acetic acid and also 0.50 molar of acetate ions. That makes that solution a what? It has a weak acid and its conjugate base, pretty decent concentrations of both of them. This is a buffer. Okay? So that's the first thing you have to check. Is this a buffer? Yes, we have conjugate. I say similar concentrations. I think I have that on a page here. The concentrations have to be 1 order of magnitude apart from each other or less. Okay, I'll show that to you. So as long as they're anywhere within the same decimal place, their concentrations are similar. Okay, so all we need is the Henderson-Hasselbalch equation. pH equals pKa log, in this case, the acetate ion okay. So it's going to be the base over the acid. Okay. What else do I need here? I've got the concentrations just straight from the problem.
The Ka value.
Yep. So Ka of what?
Acetic acid.
Oops. Lowercase a. Okay. So acetic acid, 1.7 times 10 to the minus 5. Equals, somebody punch that in?
4.76.
Yep. And that's 1.7. Yeah, 4.77 if we're doing 2 decimal places. Okay. So it's going to be 4.77 plus the log of what over what? 0.5 over 0.5. Okay. Does anybody know what the log of 1 is? Log of 1 is 0. Remember, log means to what power have we raised some base? So we raise 10 to the 0 power, that equals 1. Okay? So the log of 1 is 0. I don't know if we do this sometimes, sort of cross it out and show that 0. Okay? So that was easy.
They're all going to be that easy, right?
Oh, yeah, sure. If the concentrations are the same, what very general thing could you say about a solution if the concentration of acid and base are the same? Okay, there we go. pH equals pKa of a buffer if concentrations are the same. Concentration of HA, the weak acid, equals concentration of its conjugate base. Okay? So, that is the simplest kind of buffer to make. If you want to make a buffer that has a certain pH, find an acid with a pKa around that. If you have equal parts, the acid and its conjugate base, you will buffer it to the pKa. Okay? We then, what do you suppose we could do to adjust the pH of the buffer? Because obviously it's not always going to be exactly at a pKa that we're wanting.
Could change the concentrations of the acid.
Yeah, we could change the relative concentrations. Okay? We could change the ratio of those concentrations. More acid would make the pH go down. More base would make the pH go up. That should make sense because the log of a number over 1 is positive. Okay? That will increase the pH, right, making it more basic. If you have more acid, the log of a number less than 1 is negative. So that makes the pH smaller. Okay? So think of taking the log of that as going plus or minus based on how that fraction is weighted. Right? Where 0 is where those are equal. Okay? Going heavy on the top or heavy on the bottom will adjust the pH above or below the pKa. Okay? That's how that works. What's the formula for ammonium chloride? Regular ammonia is NH3. What is ammonium? I'll give you a hint. It's the conjugate acid of NH3. NH4. So NH4Cl is ammonium chloride, but that's actually made up of NH4 with what charge? Plus. And Cl minus. So, again, anytime we have an ionic compound, you have to write out what both of those ions are. If you are lucky, one of them will be pH neutral, and we can actually do a calculation then. Which one of those ions is pH neutral in this case?
Chloride.
Yeah, chloride is, because chloride comes from strong acid. If chloride had any pH effect, it would be making HCl, but you can't make HCl in an acid-base reaction. It would just break apart again. Okay? So, why don't you guys give this a try? Use the Henderson-Hasselbalch equation. First, ask yourself, is this a buffer? Is this a buffer? first you guys tell me this. It's going to be pH equals pKa plus log of what on top here? Yes, I'm going to put the substances, but NH3 on top, what substance is on the bottom here?
NH4.
NH4 plus charged. Don't leave that charge off. Okay. You probably get the same answer, but still, you got to have that charge. A conjugate acid-base pair, they can't both be neutral. one of them, the acid will be more positive than the base. Okay, so if
Going to be neutral, or
they don't necessarily have to be. You could have both of them be. You could have a 1 minus and a 2 minus, for instance. Okay, but they can't both have the same charge. If the acid was neutral, the base would be minus. If the base is neutral, the acid is plus. Okay? So that's a quick double check to have. They're never going to have the same charge. They're never going to both be neutral. That's important. Okay? So what are we going to do about pKa here?
1.8 of log of 1.8 times 10 to the negative 5, right?
Okay, so you found 1.8 times 10 to the negative 5. What does the table describe that value as? That is the Kb of what? Okay, that is the Kb of NH3. Kb. If we took the negative log of that, what kind of value would that be? That would be, well, it would be pKb. Yeah. I mean, it's like POH, but if we're taking the negative log of Kb, we would get pKb. Okay? So you have two options. We need pKa here. Okay? You could go about that one of two ways. What would be one way of doing that? You solve for Ka. Yep. Okay. Anybody know the other way? Yeah.
You take KW divided by KB, you get KA.
Yep. I think that was our method one. I think that was our method one, yeah. And that would certainly work. Okay. I'll give you a hint. pKa and pKb have the same relationship that pH and pOH have.
14 minus negative log.
Mm-hmm. Yep. So I don't know. I haven't typed both of those in, but I have a feeling that that might be one or two fewer keystrokes. It's probably pretty close, but so in other words, let me write what you could do. You could do Ka is Kw over Kb. pKa is negative log Ka, or you could do pKb is negative log of Kb. pKa is 14 minus. Okay, so everybody get a pKa? Yep. I got 9.25527. If you're using 1.8 times 10 to the minus 5. Okay. So we are going to be adding or subtracting from it. We have 2 sig figs, so I would write it down with 3 decimal places. I would write down 9.255. That's just so we don't have a rounding error. The 2 sig figs are the 2.5 there. But I would write down one or 2 extra sig figs there. Okay. So 9.255 is going to be where we're centered around, and then the concentrations will tell us which direction we've deviated from that. Okay? So it's going to be log of what over what? 0.15 over 0.10. Log of 0.15 over 0.10 looks like that should be a, what do you think, a positive or negative? Yeah. Taking the log of a fraction converts it into a positive or negative number depending on whether the top or the bottom is bigger. Okay? So that looks like a positive value to me, which means it will add to the pH, which again makes sense because we have more of the base than of the acid. So it's going to be a pH that's a little bit higher. Okay? So what I usually do is have the pKa value and have that be in your calculator already so that you're not making a rounding error. And then I just add log of 0.15 divided by 0.10. Okay. So what'd you get? 9.43. Yep, that's what I got. Okay, that's reassuring. Okay. Which way was fewer keystrokes? 14 minus?
Well, if you put 14 minus into like...
You can put that in first, yeah.
So I put in 14 plus...
Plus log, yeah.
KB.
That.
If you put that in one line, then it's
Yeah,
nice.
yeah. So yeah, if you did 14 minus minus, which is plus, you did 14 plus log 1.8 e minus 5. That gets you right there. Okay. So, yes, this relationship right here, pKa and pKb have the same relationship that pH and pOH have. Okay. When we defined that 14 relationship, that 14 came from, 14 is pKw, in other words. Kw is 1 times 10 to the minus 14. So 14 is pKw. So that's the ratio of, or that's the sum of the pKa values because that is the product of Ka and Kb. Okay? All right. So just a minor complication with the Ka and Kb. But, of course, if you get a little bit sloppy with this and you're not, and the mistakes, in other words, that I see students make involve interpreting the ionic compound a lot of the times. Okay? So honestly, identifying an ionic compound, one of those basic things from first semester, is actually really important to do right here. Okay? In nowhere in here did I have the chloride ion. Okay? It would actually be incorrect if you had NH4Cl right there for, I mean, it's the same substance, but when we're doing neutralization reactions here in a second, that's going to really screw things up. Okay? So it's actually important we have the correct substances. Easy way to check is that the conjugate acid and base will be only different by an H+. Okay?
Determine if they're high concentrations.
Well, relatively high concentrations in relationship to each other. Okay? So relative to each other are their concentrations high. So there is a general rule about total concentration. I might have that written down somewhere in a little bit, but in general, if the concentrations are within the same power of 10 as each other. Okay? All right. So